Okay, we're going to end our set of notes here talking about energy density and then getting a little bit into the concept of image formation. So remember I said all along that we would see mu naught and epsilon naught show up again as part of the speed of light. And it turns out that there is a relationship for an electromagnetic wave between its magnetic piece and its electric piece, and that ratio is the speed of light. So we just see this show up in the form of the speed of light is related to the permeability and the permittivity using this formula, 1 over the square root of the product of those two. So when I have an electromagnetic wave, it's two numbers, the two pieces of it aren't independent. You can't have just any electric field with any magnetic field. The two have to be related, and they're related through the speed of light. And that's all we're going to say about that. You can go into that in a lot more detail through something called Maxwell's equations, but we don't do that in the algebra-based class. So when we talk about image formation, there is a video with a whole lot of ray tracing information on it. So I'm not going to do a ray trace here. We're just going to talk about how you figure out whether it's the 3 criteria for the image. Image formation occurs when the outgoing ray of the lens or the mirror come back together in the same relative position. Now, they either really do this or they appear to do this, okay? If they really do this and the light rays actually cross again to form the image, then we say that's a real image. That's an image that has all the information that the light's carrying. It can be transferred onto film. It can be captured in a CCD. It can be projected on a screen. So that light information is carried in that image. So that's a real image. If they don't, if they only appear to cross, in other words, they actually diverge after hitting the lens or the mirror, and we have to imagine tracing them back, we say that's a virtual image. That image can only be looked at. It can't be captured on film or projected or whatever. So if you see an image in a mirror, that is a virtual image because that light can't actually get there. My cat just climbed up the bookcase and made a loud noise there. Okay, so we say that's a virtual image. So when we do ray tracing, we're going to assume we're either using a mirror or we're using a symmetric thin lens, meaning that it's the same shape on both sides. Okay, this is not like, say, a contact lens, which is curved in what's called a meniscus formation, where they're both curved the same direction. A thin lens will either be convex, where it bows out on both sides, or concave, where it caves in on both sides. All right, and we're going to ignore the thickness of the lens and not assume that anything gets absorbed or scattered by the lens. Then we have to talk about if it's converging or diverging. So diverging systems will always be diverging. Converging systems can be forced to be diverging if you get too close to them. And if you watch the video about ray tracing, you'll see the examples of that. Then when we talk about lenses, there's focal points on both sides. With a mirror, there's only a focal point on one side. So we have a near focal point and a far focal point for a lens. And I talk about that in that video. And then if we have a multiple lens or mirror system, we treat the objects we treat each piece one at a time. So we work the first problem with the first lens or mirror, and then the second part with the next lens or mirror. So what happens is the image from the first piece becomes the object for the second piece. And then we just keep working through. And I do an example of that in the notes that you can go back and look at. So as mentioned in the ray trace video, it's in parallel, out through the focal point, in through the focal point, out parallel. And you'll see what I mean in that video if you will watch that. And the focal point is if you have light coming in from very far away, like the sun or a distant star, that's where that light would focus. So if you've ever taken a magnifying glass outside and made the light beams all come together and like burn a hole in a piece of paper, that's the focal point of that lens. And then the focal length is how far the focal point is from the lens or the mirror, measured usually in centimeters. Then we need to know the image distance, the object distance, and then we'll sometimes calculate the magnification. Again, in that second video, I go through all of that. So we talk about this equation, 1 over the focal point is equal to 1 over s plus 1 over s prime, where s is the object distance and s prime is the image distance. And then you need to worry about the signs of these things. So that's where we're going to get to right now. So these sign conventions are listed here. The object distance is positive if the incident light or the light coming in and the object are on the same side. For us, pretty much that's always going to be true. It's always going to be positive. The image distance is positive if the outgoing light and the image are on the same side. So for a lens, the light will go through it no matter what. So the image needs to form on the opposite side of the lens as the object to be a positive image distance. If it forms on the same side of the lens as the object, that's a negative image distance. For a mirror, that's exactly opposite, because for a mirror, the light reflects back toward the object. So a real image will form on the same side as the object, and on the opposite side of the object is a virtual image for a mirror. So they're exactly opposite between the lenses and the mirrors. And then the radius of curvature, if it's a diverging lens, it's negative. If it's a converging lens, it's positive, and that determines the focal length, because remember, the focal length is 1/2 the radius of curvature. All right, so that's the last of those notes. So we will stop here, and I'll put this up, and you should have all the notes that you need. There's a lot of notes and a lot of problems here for you to look at, so I hope you get to look at all of them.